Hello, my name is Christopher Alfonso, and this presentation is titled The Influence of Dynamic Topography, Climate and Tectonics on the Nile River Source-to-Sink System. The presentation is a brief summary of the research I undertook for my honours degree at the University of Sydney in 2020, under the supervision of Tristan Saul, Claire Mallard and Sabine Zahirovic, and with assistance from Peter Lovely and Laura Hubner-Diaz of Chevron. The project involved modelling the evolution of the Nile River system and the topography of northeast Africa over the past 40 million years. The research was primarily focused on exploring the role played by dynamic topography, but it also encompassed the tectonic and climatic history of the region. In this talk, I'll provide a brief introduction to the Nile and its context, explore some of the data which was incorporated into our numerical landscape evolution models, and summarize the most significant findings of the project. With a length of more than 6,000 kilometers, the Nile is one of the longest rivers in the world. The river's size and its rich resources, including fresh water, hydroelectricity, and major hydrocarbon reserves, provide a strong motivation to deepen our understanding of its history. At the present day, the Nile is primarily fed by three main tributaries: the White Nile, which drains the African Great Lakes region, and the Blue Nile and Atbara River, which both drain the Ethiopian plateau. The Ethiopian rivers contribute the majority of the Nile's yearly flow and sediment flux, at 70% and 96% respectively. The dominance of these two rivers is largely due to the extremely high rainfall on the Ethiopian plateau. The White Nile, meanwhile, loses much of its sediment load in swamps and marshes before it reaches the main Nile trunk. The precise age of the Nile River is uncertain, although the majority of recent evidence points towards an ancient origin around 30 to 40 million years ago. The incipient Nile Delta began to form near Cairo in Egypt approximately 35 to 38 million years ago. Meanwhile, zircon grains derived from the Ethiopian plateau began to appear in the delta essentially as soon as they formed, around 31 million years ago. And finally, the Blue Nile Gorge, a dramatic erosional feature on the Ethiopian plateau created by the Blue Nile, began to be formed around 25 to 29 million years ago. The remarkable longevity and stability of the Nile, apparently remaining essentially unchanged for at least 30 million years, may be explained by the existence of a large dynamic topography gradient beneath northeast Africa. This gradient consists of dynamic subsidence to the north, caused by the long-lived subduction of the Tethys Ocean, and dynamic uplift in the south, associated with the Afar mantle plume, currently located in East Africa. The arrival of the Afar plume head beneath present-day Ethiopia, which occurred around 31 million years ago, was responsible for volcanism, which resulted in the eruption of a 4-kilometer thick flood basalt pile. This material, dynamically uplifted by the mantle plume, formed the Ethiopian plateau, and this plateau has since experienced extensive erosion after its formation, providing huge volumes of sediment to the Nile River and creating dramatic river valleys like the Blue Nile Gorge mentioned earlier, shown here on the right. In order to investigate the history of the Nile, this project made use of the Badlands Numerical Landscape Evolution model. This model simulates Earth's surface processes such as erosion and deposition, incorporating a range of forcing conditions as model input parameters. These include topography, lithology, tectonic, dynamic and flexural uplift and subsidence, spatially and temporally variable precipitation, and eustatic sea level changes. In the next few slides, I will outline some of the most significant input parameters for the models used in this study. The initial topography for the models was primarily based on present-day topography taken from the eTOP01 digital elevation model. This topography was modified by removing sediments deposited since the model start time at 40 million years ago, and reversing the effects of tectonic activity and dynamic topography. The results of this process were then evaluated by comparison to an existing global paleotopography model before being used as model inputs. Meanwhile, the paleoprecipitation data used in the Badlands models was extracted from a global paleoclimate reconstruction. This was then modified according to local paleoprecipitation proxies for parts of the study area where data was available, creating the final result shown here. A simplified lithologic map for most of the study area was created by compiling country-level data such as maps published by geological surveys. From this, a map of relative erodibility was created using a simple lithology-dependent conversion factor. Flexural isostasy was simulated using a lithospheric elastic thickness map extracted from a dataset covering the entire African continent at present day. The relatively thin lithosphere beneath the Red Sea and Arabia, as seen in the map on the right, was removed for the portion of the model before the formation of the Red Sea Rift at approximately 20 million years ago, resulting in the map on the left. This allowed for the modelling of lithospheric thinning associated with the rifting process. As dynamic topography was the primary focus of the project, two different dynamic topography reconstructions extracted from global geodynamic models were tested. These two models were referred to by their creators as M5 and M2, and these names were used here as well. A third scenario was also created as a hybrid of the other two models, and shown on the right. The hybrid scenario incorporated the most distinctive elements of both models: the strong and widespread subsidence signal from the Tethyan subduction found in model M5, and the well-defined Afar plume uplift signal, which is the most significant feature of model M2. The modeled topography and drainage networks for the M5 and hybrid dynamic topography scenarios are shown on the right. While these two models produced broadly similar results, the model using the M2 dynamic topography scenario, which prominently featured the Afar plume, did not produce any river system which resembled the Nile. For this reason, subsequent analysis was largely focused on the M5 scenario, which did not include an Afar plume, and the hybrid scenario, which did. The modeled Nile Delta sediment distribution for the hybrid dynamic topography scenario is shown on the left. The M5 scenario also produced a similar pattern. Comparing the model results to the sediment thickness map shown on the right, derived from seismic data, shows that the two are in good agreement, with sediments primarily divided into two sub-basins controlled by the pre-existing bathymetry of the eastern Mediterranean Sea. Modeled sediment thicknesses were slightly lower, however, with a maximum thickness of 4 to 5 kilometers compared to the true value of 5 to 8 kilometers, perhaps suggesting a wider dispersion of sediments in the model. Sedimentation rates within the Nile Delta for the two scenarios show very similar trends through time, though the M5 scenario without the Afar plume shows significantly less variability and consequently produces a larger total sediment volume for the Nile Delta. Comparing modeled Nile Delta sediment volumes to volumes calculated from the sediment thickness map shown earlier reveals that the hybrid scenario, including the Afar plume, reproduced the calculated total sediment volume of just under 800,000 cubic kilometers fairly well, as shown above. Meanwhile, the M5 scenario, without the Afar plume, produced far too much sediment in the Nile Delta, well in excess of 1 million cubic kilometers. The Nile Delta sedimentation history for the hybrid scenario, shown in more detail below, also allows the identification of some of the most significant events in the river's history. The dramatic pulse of sedimentation coincident with volcanism on the Ethiopian plateau suggests a strong relationship between the river and the plateau. Following the end of Ethiopian volcanism 25 million years ago, it is also possible to identify the uplift of the Red Sea hills on the shoulder of the Red Sea Rift starting 20 million years ago, the weakening of the Afar plume dynamic uplift beginning around the same time, and possibly also the formation of the Sahara Desert approximately 12 million years ago. Cross-sections through the modeled Nile Delta were also created, revealing the delta's synthetic structure as shown here with sedimentary strata colored by their depth of deposition. Due to the lack of major tectonic activity in the Nile Delta region during the time frame of the models, this stratigraphic structure was controlled largely by eustatic sea level variations. Accordingly, models run using a constant sea level value produced an essentially featureless delta lacking any such stratigraphic structure. The volume of sediment provided to the modeled Nile by several different regions was extracted from the model results. In agreement with the situation at present day, the modeled Nile system was dominated by sediments derived from the Ethiopian plateau ever since the eruption of the Ethiopian flood basalts beginning approximately 30 million years ago, with only negligible sediment contributions from the other regions. These results indicate that the eruption of the Ethiopian Plateau flood basalts was by far the most significant event in the history of the Nile and its delta, since the plateau provided and continues to provide the majority of the river's sediment. Dynamic topography, meanwhile, may have been crucial to the Nile's formation. The dynamic topography gradient, suggested to be the reason for the Nile's stability, appears to have also been required for such a long river to form in the first place. The lack of a Nile river in the models using the M2 dynamic topography scenario, in which this gradient is not as pronounced, supports this hypothesis. The motion of the Afar plume relative to the upper Nile catchment may have also played a role in the river's evolution, especially in the absence of any major tectonic activity in most of the Nile catchment during the last 20 million years. Finally, this project also served as a demonstration of the potential of complex landscape evolution models such as the ones developed here. These models can incorporate a wide range of tectonic, topographic, and climatic data.